Hi guys, very good evening. Myself Dinesh. Welcome to BYJU'S Exam Prep, India's most comprehensive exam preparation platform. So in yesterday's session, we have talked about differential pulse code modulation. So in today's session, we're going to talk about delta modulation. The discussion will be similar to DPCM, but there are a lot more things to understand apart from DPCM. Right. So what is the agenda of today's class? So before talking about the agenda, let me give my introduction. So I have 10 plus years of experience. I have done my masters from IIT Madras with specialization communication systems. So I teach these subjects communication systems and signals and systems. So this is my Telegram group. So if you wish to ask me any doubts based on these two subjects or any other general questions, you can contact me on this group. And I used to work for most reputed institutions in the country for the last 10 years, and I've cracked GATE twice. Right. So what is the agenda of today's session? So we'll be talking about the most important discussion that will happen in today's session is the discussion about delta modulation. So before talking about delta modulation, I'll talk about the previous session homework questions answers. One question I've given as homework in the previous session. Only one question because numericals are very less likely in DPCM. So and after that, after discussion of delta modulation, at the end I'll give you some homework questions regarding delta modulation. Right. So and tomorrow's session will be practice on delta modulation. Whatever we are going to understand today, that will help you to solve problems based on delta modulation. So tomorrow we'll discuss all the models of problems based on delta modulation. Okay. Right. So this is the question that I've asked in yesterday's session. It's a simple question actually, but I did not reveal you what is the data rate in DPCM. So that is the only tricky part. If you know that, if you know the formula for data rate, bitrate or data rate in DPCM, it's a very simple question. We have done similar kind of questions in the previous classes also. But only thing is, I did not talk about DPCM bitrate in yesterday's session. I have given you that as homework. Okay, right. So just to talk about bitrate, let us understand what is the bitrate in DPCM. So here we are having message signal m of t. M of t is sampled. We are having m of nts, and here since for a sampled signal, the important parameter is the number of samples present for every second. So the important parameter for this signal is sampling rate, fs samples per second. And here in PCM system, this feedback circuit is not there. So whatever samples are there, those are applied to quantizer. Okay, and quantizer, every sample given to quantizer will also give one sample. So fs number of samples per second given to quantizer, and quantizer also used to give fs number of samples per second. That is what is happening in PCM. But what about in DPCM? In DPCM, the sample here and the sample here are different. But one sample here will give one sample here. Correct or not? The sample here, the value, amplitude of the sample is different from here and here, but number of samples is same here and here. For every sample that comes here, there will be one sample here, because what happens is here, plus and minus, the difference happens. The feedback sample comes, this present sample and the previous sample difference is given as input to quantizer. For every sample given here, one difference will come here. So if there are fs number of samples per second, there will be fs number of samples per second here also. And we have discussed in previous classes that quantizer, it will not eat away samples or it will not increase the samples. Whatever number of samples are given to quantizer, what does quantizer do? It will approximate the amplitude. It will approximate the amplitude and it gives the sample at the output. Any number of samples given to quantizer, it will just approximate all the voltages to the closest quantization levels and it will give us output. So one sample given to quantizer, one sample will be coming as output of this quantizer. So if fs number of samples per second are given as input to quantizer, output also will have fs number of samples per second. And fs number of samples are given as input to encoder. We know what an encoder does. One sample is converted to n bits. That is the job of a quantizer. Encoder does conversion of one sample, every sample, into n bits. So if we are having fs number of samples, they will be converted to n fs bits. but we are not having fs number of samples, we are having fs number of samples every second. So we are going to have n into fs number of bits every second. So this is what we are calling as bit rate, right? And what is the formula for bit rate in DPCM? It is exactly same as bit rate in PCM, which is n times fs. Same formula, no changes. The feedback circuit changed, but the number of samples did not change. So the formula is exactly same. Okay, I hope everything is clear till this point. Right, so coming back to the question, now it becomes a simple question since we know the bit rate of DPCM system. So let us calculate sampling rate. How much is that? Sampling rate is equal to 75% higher than Nyquist rate. Original Nyquist rate is 100% if you can think. Then 70% higher means it is 175% of Nyquist rate. It is 75% higher than Nyquist rate, which is same as 175% of Nyquist rate, which is equal to 175% converted into normal scale is 1.75 into Nyquist is 2b and bandwidth is 10 kilohertz. So which is equal to 1.75 into 2 is 3.5, 3.5 into 10 is 35 kilohertz or kilo samples per second, you can say. That is the sampling rate. And bit rate is equal to NFS. Whether it is PCM system or DPCM, the formula for bit rate is same, and that is N is 5 and Fs is 35 kilo, which is equal to 30 into 5 is 150, 5 is 25. It is 175 kilo bits per second. Is that okay? Yes, I think that should be correct. Fine. So one student, the same student who was giving the answers, the same student has given the answer in the comment section. Others who have solved also can answer in the comment section, at least starting from today's session. Right. So that's the thing with the homework question. We have done the solution. We got the answer. So if you have done it, you can cross check the solution. Right. Next, let us start with the most important concept that we are supposed to discuss today, and that is delta modulation. So this is delta modulation transmitter circuit, and this is delta modulation receiver circuit. So have you observed something here? Is there some similarity from yesterday's session? So sir, you are saying that this is delta modulator transmitter circuit. Yesterday also we have seen the same circuit. You might say, yes, you have seen yesterday. By mistake, I am not showing this diagram. Yes, this is the exact circuit that we use for delta modulator also. So if it is exact same circuit, then we should not call it as delta modulator, we should call it as DPCM, no? What is the difference? Yes, there is a small difference. There we were using n-bit encoder. There we were using n-bit encoder or n-bit quantizer. We can also call quantizer as n-bit quantizer or 2 power n level quantizer. 2 power n level means 2 power n quantization levels. So quantizer can be sometimes called with the number of bits that are being used for encoding or number of quantization levels being used in quantizer. For example, there are 8 bits used in a PCM system. Okay, then we can call it as 8-bit quantizer. We are using 8-bit quantizer, or we can also call it as 256 level quantizer. In questions, you might see both the cases. They might say 8-bit quantizer or 256 level quantizer. Both are same informations, right? So the only change between DPCM and DM, delta modulator, is instead of n bits, we are going to use 1 bit. Without any confusions, we are going to use only 1 bit encoder. So 1 bit encoder means we are going to have 1 bit quantizer, or you can say 2 level quantizer. 2 level quantizer or 1 bit quantizer. That is the only difference. Okay, there definitely in DPCM we definitely are not going to use 1 bits. We are going to use higher number of bits, 5, 6, 7, 8 or anything more than that also based on the requirement. So if you are using only 1 bit for encoding, then we can call it as delta modulation. DPCM system with 1 bit encoder or 1 bit quantizer, we can call it as delta modulator. So delta modulator is a 1 bit, it's a 1 bit DPCM system. Okay, fine. Circuit is similar. Okay, our analysis, whatever analysis we have done yesterday, the same analysis is applicable here also. Okay, let us recollect few points. Okay, let us recollect few points. Whatever analysis we have done in DPCM, same analysis will apply here. So whatever points are useful in yesterday's discussion, let me quickly revise them. So we're going to have the samples here, and we are going to have in the feedback we'll have quantized versions of previous samples. Here we'll have present sample, and here in the feedback we're going to have the previous samples. It's a plus and a minus. So this circuit will generate the difference between the present sample and the feedback sample. Present sample and feedback sample, or what is the feedback sample? It is the past sample, just the previous sample. Okay, so present sample and quantized version of a previous sample will take the difference of it, and that difference is being quantized. Okay, that quantized difference is being encoded and transmitted. Okay, since it is only a 1-bit encoder, only one number of bits used is only 1, which means 1 or a 0. Every voltage that is present here, or every difference that is being quantized here, is being converted to either 1 bit or a 0 bit. Okay, let me quickly draw the characteristics here. How the characteristics look like? Since it is a 1-bit quantizer, only 2 levels will be there, and the 2 levels are going to be designed like this. So it is delta and minus delta as a function of x. This is y. So input versus output characteristics. If x is the input to the quantizer and y is the output of the quantizer, x versus y characteristics. Or you can also simply write it as, since I have not mentioned anywhere x and y, input to the quantizer and output of the quantizer. Okay, right. So this is how the characteristics will be. Try to understand these characteristics carefully. We'll understand that. So before that, let us recollect one more point that we have discussed in yesterday's session, and that is, whatever is the signal that we are going to receive at the receiver, at the delta modulator receiver or a DPCM receiver. In DPCM receiver, just before low pass filter, whatever signal we are going to receive, that signal is same as the feedback signal here. Do you remember that point? I have stressed on that point in yesterday's session. Whatever we are going to receive here, not the final signal, here we will have an analog signal, but here we'll have a kind of a staircase kind of waveform here, which will contain the quantized samples that we are going to see in the feedback. So the signal here is exactly same as the signal that we see in the feedback of the transmitter circuit. Okay, that is a very important point. How we have seen that in yesterday's session. Today's session also we'll see that, we'll observe that. Okay, that is a very important point. The signal that you are going to see here is same as the final signal just before low pass filter. Whatever signal you are going to receive at the receiver, that is same as the feedback signal. Why is that point important? Because, well, let's try to analyze this signal, the feedback signal. It is as good as analyzing the received signal. We can compare. We know what is the transmitted signal, and we can understand what will be the received signal by analyzing the feedback signal. Then we can compare them. Okay, whatever we are going to receive at the receiver, that we can see in the feedback at the transmitter itself. By looking at this and comparing with the original signal, we will understand what kind of quality is maintained in the process of delta modulation. Okay, one more point I want to stress here. We are always calling it as a modulation, right? Differential pulse code modulation, delta modulation. Are these modulation techniques? No, they are not modulation techniques. Somehow they have named it with the word modulation. Modulation means change. Generic meaning is change. If you change it, we call it as modulation. But in communication system, the meaning of modulation is shifting the signal's frequency from low frequency to high frequency. That kind of modulation is not happening here. Okay, the modulation definition that we use in communication, that is not happening here. In delta modulation, there is no modulation happening. We're only doing analog to digital conversion. Okay, all these 4 techniques, PCM, DPCM, delta modulation, adapt to delta modulation, all these 4 techniques, they are basically not modulation techniques. Though the word modulation is there, they are not modulation techniques. They are just analog to digital conversion techniques. Mind this point. Okay, fine. So let us analyze now what happens in deeper manner. In every stage what happens, let us try to analyze. You have to understand very carefully now. We are getting into the details of it. How good you understand this decides how good you are going to solve the questions. message signal m of t, and here we're going to have m of nts. Okay, and what are we going to have here? M of nts. In the feedback we are going to have m of n minus 1 ts, the previous sample, m of n minus 1 ts, and here we are going to have the subtraction of these two, and here we are going to have the approximated version of this, and that will be encoded, right? So just for your understanding, I have written this, but this will waste our space. This is not required here. Let's remove this. Okay. Now let me take some signal. Understand carefully. Some shape I'm taking just for analysis as a function of time. This is the red signal is message signal m of t. Now I'll take, okay, right. Now let us clearly try to understand. Now we are going to have samples here. What are those samples? Let me select those samples. First sample, second sample, third sample, and let me take this shape in a little different manner. Okay, fine. Now let us analyze. Now the first sample is this value. I am not taking any values for the samples. I mean whether it is 2.1 or 3.1, I am not taking it because that is not necessary here. In yesterday's session I have taken because for better understanding the values of the sample is important. Here it's not necessary to understand the sample values need not be taken. So we can understand without sample values also we can understand. Right. So before getting into the discussion of what happens in the circuit, first quickly let us understand what is happening in the quantizer. What does a quantizer do? We know what a quantizer does. It does some kind of approximation, and whatever is the behavior of the quantizer or whatever is the design of the quantizer, that we can understand using quantizer characteristics. And quantizer characteristics are very simple because it's a 1-bit quantizer. It will have only 2 levels, and this is how the design is. And what does the design say? When you give input voltage as a positive, if input to the quantizer is positive, if input is positive, what is the output? Can anyone tell me? If input to the quantizer is positive, see the characteristic, if the input is positive, any positive value, output will be delta, right? And how about if input is negative? If input is negative, then output is minus delta. Correct? That is the behavior of quantizer. If you give any negative value, smaller or bigger, output will be minus delta. If input is any positive value, bigger or smaller, output will be plus delta. So the possible values here are plus delta and minus delta. So what does encoder do? It converts the samples into bits. How does it convert? It has to have some criteria, right? It means it has to have some mapping. What sample should be converted into what bits? There should be some understanding for the encoder, right? So there are 2 possibilities, delta and minus delta. So encoder should have some idea beforehand on how the conversion should be done. The sample to bits conversion, how it should be done. And let's say it is being done like this. Delta is being converted to 1 bit. Because there is only 1 bit encoder, either we can use 1 bit or a 0 bit. Only 2 possibilities. So delta is being converted to 1 bit and minus delta into 0 bit. So whenever we get a delta output here, so encoder will convert into 1 bit. Whenever we get a minus delta output here, encoder will convert into 0 bit. As simple as that. So I believe the quantizer part is clear. Very simple discussion. Observe this carefully. Right. Every point that I've discussed till now is very, very important. So everything I'm gonna use now. Right. So whatever is the feedback signal, that I'm gonna plot here. because whatever the feedback signal, if I plot it here, then I can compare with this and we can understand how good a quality signal is being conveyed using delta modulator. Because the delta modulator or DPCM, because quantizer is there, quantization error will be there. Because of quantization error, definitely there is effect on quality. Because of that effect on quality, is the quality being a lot disturbed or slightly disturbed? We have to understand that, right? At the receiver, if you're able to get back the signal which is very close to this signal, then we are happy with the technique. But if the signal that we received at the receiver is very much distorted compared to this one, then we are not happy with the performance of this circuit, right? So to understand how good this circuit is performing, we have to compare the transmitted signal with the received signal. So transmitted signal, we are having it here itself, and we know whatever is the signal in the feedback, that is same as not the final signal, but just before final stage, before the low pass filter. In the receiver circuit, just before low pass filter, this is the final signal. Here we are expecting m of t. Are we going to get m of t? No, we are going to get some kind of approximated version of m of t because of quantization error. M of t and m cap of t, they might be very close or they might be slightly different based on how good we design this delta modulator, right? We are expecting m of t here, but we may not get exact m of t, but a slight distorted version of m of t. But that m cap of t, before passing through low pass filter, before smoothing, we'll have some kind of staircase waveform, as we have discussed in yesterday's session. Some kind of staircase waveform will be here. That waveform is same as the signal in the feedback in the transmitter circuit. So the signal here is same as the signal here. Okay, the signal here and the signal there will be same. So that's why if you can analyze this one, I'll plot whatever is the signal that is going to be here, I'll plot it here. Then we can understand at the receiver, are we going to receive a good quality signal or a quality lost signal? We will understand now. We'll understand further. So let us deep dive into the discussion. Right. So the first sample, is it a positive sample? Yes, no. Initially the circuit is addressed. The feedback sample is 0. The feedback sample is 0. The feedback sample is 0. And how about the first sample? Just understand carefully. First sample is some positive value, something like 1.5 or something like that. The sample here is positive, and here it is 0. We just need to understand whether the difference is positive or not, because quantizer gives a different output for positive value and gives a different output for negative value. We just need to understand the value here, the difference that we are going to have here. Will it be positive or negative? Only that much we have to understand. Okay. So let's understand if the difference here is positive or negative for every sample that is coming in. When the first sample comes in, when this first sample comes in, the first sample is positive. Positive sample minus 0 is positive. How about the first difference? It is positive, no? First sample is coming here, which is a positive sample. Minus 0 is positive. Next, if there is 0 here, it is 0 here only, here also. Now, when the positive sample is given as input to quantizer, what is the output? It is going to be delta, correct or not? Because we know the quantizer character, if input is positive, output will be delta. If input is negative, output will be minus delta. Right. This delta will be converted into 1 bit. Right. Right. Now this delta comes here also. This delta comes here, and we know we are going to do addition here. Same circuit as DPCM circuit. So delta plus 0 will be delta here. And delta, after delaying by TS seconds, we'll get delta here. And the same delta, we know the flow of the circuit. This is how the flow. Same flow as DPCM. No change. It goes like this. And the signal here goes like this and this. Right. Now, this delta will come here and it will go here after TS seconds. Now, we know the signal here, right? We know the feedback signal. So, let me plot the feedback signal. So, try to understand the feedback. It's not a sample, it's some kind of staircase waveform. It stays at delta for the next TS seconds, because for the next TS seconds, the next sample will not come. Till that time, this sample will stay here. Right. So, it will be right in the feedback after TS seconds. After TS seconds, this is, let's say, TS. Let me say this is 2 TS. This is 3 TS. and so on. Right, at TS seconds, in the feedback, I'm trying to plot the feedback signal. What is the feedback signal? It is delta. How much is the delta size? That we have to design carefully. Just for explanation sake, I'm taking some value for step size, some size, maybe this level of size, this size I'm taking. I'm not taking any values, 2 volts or 3 volts, because if you take exact values, then it will create more confusion. But here, whatever you need to understand, you can understand it very clearly with the way I'm explaining. So I'm taking some rough size for delta. But the importance in delta modulator is how you design this delta. Okay, so we'll talk about how we have to design the delta. First, let us understand what is happening in the circuit. Then we'll understand the importance of delta. Then we'll understand how to design that delta for best performance. Right, so that delta, let me take some size like this. Right, and that delta, it is going to stay like this for next TS seconds, correct? Now, next sample, when the next sample comes in, the second sample which has come here, and the feedback sample is delta. Let me write it here. It is delta. It is delta. In the feedback we are having delta, and the sample present here, is it more than delta or less than delta? That is what is important for us. If this sample is bigger than this one, then the difference will be positive. If the sample here is less than delta, then this will be negative. So here, if you are having a sample greater than delta, we'll have a positive difference, and here the sample, if the sample here is less than delta, we'll have a negative difference. Right, understand carefully. Right, so the present sample, the second sample, is definitely bigger than delta. Is definitely bigger than the feedback. So present sample is greater than the feedback. So the difference, can you tell me if the difference is positive or negative? Anyone? Second sample is definitely greater than the feedback. Second sample is greater than feedback. Bigger sample here, smaller sample here. So difference will be, it will be definitely positive, right? It should be positive. So if it is positive, output of quantizer will be delta. Output of quantizer can be only delta or minus delta, only two of them. So delta, if it is given input to encoder, we'll get 1 bit, because that is how it is, the encoding is being done. Right, so that the same delta comes here. The same delta comes here, and delta, and already delta is here. Delta plus delta will become 2 delta. So 2 delta comes here after TS seconds, and 2 delta goes here, and 2 delta goes here. Right, so the feedback, the signal that we are having is 2 delta. So 2 delta will be something like this. Something like this. This is 2 delta. Now, third sample here and 2 delta here, which is greater. Third sample is greater than 2 delta. Third sample here is greater than 2 delta. So the difference will be this minus 3 delta, sorry, this minus 2 delta, the difference is positive. So here it will be positive value, positive difference. We don't need to know exact value, we just need to know whether it is positive or negative. If it is positive here, the output of quantizer will be delta, and here also it will be delta. Delta plus 2 delta will become 3 delta, because it is addition here that is happening. 3 delta. 3 delta comes here, 3 delta goes here and here, okay, and 3 delta is here. Next, so in the feedback, what signal we are having is 3 delta. So the signal that we are having here is 3 delta. This signal, the blue signal that I have drawn here, is the feedback of transmitter, which is exactly same as input of low pass filter in DM receiver, correct? In DM receiver, whatever is the input to low pass filter, it is same. Right, so in the feedback what we are having now, it is 3 delta. So 3 delta, how does it look like? So 3 delta, I'm plotting. So this is 3 delta. Now the discussion, same discussion, but things will change slightly. Now whatever is the sample here, the fourth sample here is smaller than 3 delta, correct or not? 3 delta is bigger, the feedback sample is bigger. Whatever we are subtracting, that is bigger than the present sample. So the difference, this minus this, the difference will be positive or negative? the difference will be negative, right? It will become negative. If it is negative, it will be minus delta here, right? And it will be minus delta here. Okay, so minus delta plus 3 delta, it will become 2 delta, and 2 delta comes here after ts seconds, and the same 2 delta goes here, and it goes here as well. So 2 delta, the feedback signal is 2 delta. Let me plot the feedback signal. It is 2 delta. This is 2 delta. Next, what is happening in the next phase? The present sample is smaller than the feedback sample. So 2 delta is bigger. This 2 delta is bigger than the present sample. So difference will be negative. So here it will be minus delta, and here it will be 0, 0, because earlier 3 ones, right? First 3 ones will be there because 3 deltas are converted to 3 ones. 2 minus deltas are converted to 2 zeros. This minus delta comes here, and it comes, this minus delta plus 2 delta will become delta. 2 delta plus minus delta is delta. Delta comes here, delta goes here, delta goes here. In the feedback we are having delta, something like this, and it goes on like this. Are we getting some reasonable signal at the receiver? Whatever signal you are seeing here, the blue signal, is same as whatever we are going to receive at the receiver just before low pass filter, just before smoothening. Now this is the signal that we are receiving and at the receiver before low pass filter. Now if you pass this through low pass filter, what happens? If you pass this through low pass filter, are we going to get some signal which is similar to the red signal? May not be exactly same as the red signal, but we get some kind of close signal, right? Correct or not? So if you smoothen this waveform, we get some shape which is close to this red signal. May not be same as red signal exactly, but similar one. Okay, if I send my voice signal, that exact same voice signal will be replicated if this is what is happening. But will that happen practically? May not be. What happens practically? What challenges we are going to face practically? That we are going to discuss in the next few slides. So the signal that I've taken the signal in such a manner that things will work out very well. It looks like delta modulator is performing wonderfully well, but things will not work in the same manner that we have discussed in this session or in this slide. But the reason why I have taken a simple signal is just to convey how the circuit is working. My intention is not to talk about what are the flaws of delta modulator. In this slide, my intention is for you to understand what is happening at each and every stage. Once we have understood that, the next stages, in the next slides, we are going to talk about what is the problem with delta modulator. If I am taking some other kind of signals, will the delta modulator perform the same way, or will it have some problems? We'll talk about that in the next slides, right? So anyway, so we have talked about transmitter, delta modulator transmitter part. We'll talk about the receiver also first. We'll talk about the receiver also quickly. It's easy part, same as DPCM. And after that, we'll talk about the difficulties that we face in delta modulator and how we can overcome them. Right. So I hope everything is clear till this point. Right. So what did we transmit? We transmitted 3 ones and 2 zeros, right? Now 3 ones and 2 zeros. 3 ones and 2 zeros. We have transmitted. Let's say we have received the same 3 ones and 2 zeros. And what does the decoder do? One is converted into delta. Okay, first one is converted into delta. In the feedback we are having 0 initially. 0 plus delta is delta. After delaying, we'll get delta only here. So the signal here, let us plot it. It's delta. And after that, this delta comes here and the feedback. So by the time after ts seconds, this delta comes here, and by the time it comes here, the next sample will come here. The second bit is converted into again delta. So delta plus delta will become 2 delta. This delta here, because of second bit, delta will come here. Because of the feedback, another delta. Delta plus delta, addition will happen here. Delta plus delta will become 2 delta. 2 delta comes here in the feedback. The signal here and the signal here, it's same because of the same circuit. There is nothing in between. So it is 2 delta. Next, what happens next? So third one is also being converted to delta, because delta is converted to 1 and minus delta is converted to 0 at the encoder part. So decoder will do exactly the opposite. So, and the remaining 2 zeros will be converted to minus delta and minus delta, right? So, third delta came here. By the time third delta came here, we are having 2 delta. 2 delta plus delta is 3 delta. 3 delta will be here, and signal, if you plot whatever is the signal here, we'll get some signal like this, 3 delta. Next, 3 delta will come here. By the time 3 delta comes here, which is the third sample, so fourth bit will be converted to minus delta. So minus delta is here and 3 delta is here. By the time minus delta is here, we are having 3 delta here. Minus delta plus 3 delta is 2 delta. So 2 delta will be here after TS seconds. So the signal here will be 2 delta, something like this. The 2 delta, by the time 2 delta is here, this minus delta will be here. The fifth sample will be here. By the time fourth sample is here, fifth sample will be here. Minus delta plus 2 delta will become delta. So here it will be delta after TS seconds, something like this. Now if you smoothen the waveform, if you smoothen the all the discontinuities will vanish, and the signal will become smooth signal. So the simplest way of saying it is just join the midpoints of the staircases, you'll get the smoothened signal. If you join the midpoints, you'll get some signal like this, which is roughly close to the original signal that we transmitted. Does this happen always in delta modulator? No. It does not happen always. It does not happen many times. Most of the times it does not happen. Which means delta modulator we may not be able to reconstruct the original signal exactly same in most of the cases. Why? We'll talk about that. So why it does not work? We'll see in the next slide. Practically, I'm talking about practically. Why it does not work is it does not work practically. Theoretically, it might work for some signals, but for many signals it will not work. Why? The reason is, we'll understand that in the next slide. We will understand a lot of things in the next slide. So we have understood how the delta modulator works. We have to understand what are the problems with delta modulator. Under what situations delta modulator will fail, or for what kind of signals it will fail, or for what kind of signals it will pass. Okay, it will pass means it will work well. Very good. So let's understand same delta modulation. I'm taking different signal here. Whatever analysis we have done in the previous slides, same analysis we'll do here, but we have to do it little quicker. We should not take more time here. We have to do it little quicker. So let's do it. So I'll take some signal. Something like this. I'm taking some signal. We'll analyze what is happening to the signal in the circuit. Then we'll see some problem is happening, some distortion is happening at the receiver. The received signal at the receiver and the transmitted signal, they'll be different, completely different. And why is that different? What problems are being faced in the circuit? We'll understand. Right. Same analysis that we have done previously. Okay. Right. Let me take the first sample. Let me select the samples here at TS seconds. Let me take some step size. Okay. So initially the circuit is at rest. There's a plus here and a plus here. Initially the circuit is at rest. We're going to have 0 here. So come on, let me just quickly tell me. So what is happening here? The first sample is positive. Positive sample minus 0. It will be positive here. Right? If it is positive here, the output of quantizer, 1 bit quantizer characteristics we know, we have plotted previously. For positive values it will give delta, and for negative voltages it will give minus delta. This is the characteristics of 1 bit quantizer, 1 bit encoder. Right. When the input is positive to quantizer, the output will be delta. Delta will be converted to 1 bit, and this delta comes here. It's a plus here and a plus here. Initially it is 0 here. 0 plus delta will become delta. So the output of delay circuit will be delta. Okay. So now the feedback signal is delta. Let me plot the feedback signal. The feedback signal is delta. At TS, the feedback signal is delta, and it will stay there for TS seconds. I'll take same step size that we have taken in the previous case. Next, this is delta. Next, Next sample, the second sample is greater than delta, definitely. Second sample is greater than delta. So this minus this sample, present sample, minus the feedback sample, difference is definitely positive, right? Difference is definitely positive. If the difference is positive, when the next sample comes here, when the second sample comes here, the difference is positive. So we'll get again delta here, 1 here, the same delta comes here, and that delta, previously we were having delta here. So we know the flow of the circuit. In the previous case also we have discussed the same flow. Whatever signal comes here, the delta came here, it went here, it went here. Now for the second sample, we are having positive value here, delta here, and by the time delta is here, another delta is here, delta plus delta will become 2 delta. That same 2 delta will come here and it will go here. So the feedback signal will be 2 delta. The feedback signal will be 2 delta. It is 2 delta. Okay. Next, third sample. Third sample, is it greater than 2 delta or not? Third sample, is it greater than 2 delta? Yes, it's hugely greater than 2 delta. So the difference is hugely positive. We are not bothered about whether it is huge positive value or a small positive value. If it is positive or not, that is what is important in delta modulation. So it is positive value here. So if it is positive, it is delta here. Okay, and delta comes here, and delta plus 2 delta will become 3 delta here. 1 goes here. So 3 delta comes here, 3 delta goes here, and here also, right? So in the feedback we are going to have 3 delta. We are going to have 3 delta, right? Next, this is 3 delta. Next sample, similarly, if I think you can analyze, next difference is also positive. Next sample is greater than the feedback 3 delta. So next also will be positive. Next also will be positive, and here it will be delta. Delta plus 3 delta is 4 delta. 4 delta comes here, 4 delta goes here and here. Okay, right? So it will be 4 delta here. Let's plot the 4 delta here. Okay, now just see the difference. They are very close, but the present sample, this one, the present sample is greater than the feedback. The present sample is greater than the feedback. See, the present sample is greater than the feedback. So the difference will be again positive, small positive value, but it is a positive value. If it is positive here, we'll get delta here, delta here. Delta plus 4 delta is 5 delta here, 5 delta here. Five delta here and here. Okay, so if 5 delta here, so let's plot what is happening in the feedback. We got 5 delta signal, so this is 4 delta. So next signal will be 5 delta. Okay, now say this one. So next sample is smaller than the feedback. Feedback is 5 delta. Next sample is smaller, so difference will be negative. Negative here, it will be minus delta here, minus delta here. 5 delta plus minus delta is 4 delta here. So 4 delta here, 4 delta here and here. Right, so it will be 4 delta. Now what is happening to the difference? Present sample is greater than the feedback, so difference will be positive now. So it will be plus delta here. So plus delta plus 4 delta is 5 delta. This is 5 delta here. So 5 delta here, 5 delta here and here, right? So again, so signal goes like this. This is what is happening. Same analysis we have done, same analysis. Okay, wonderful analysis actually. So we understood the previous discussion, the same discussion we have done here, but for a different type of signal. So if you try to reconstruct this signal, if you try to join the midpoints, are we getting the same signal? No, right? We are not even getting a closed signal. We are getting a lot distorted signal. You can say a lot different signal you are getting, which means quality is distorted a lot. Okay, which means for all signals, delta modulator may not work fine. Okay, in what cases it will not work fine, we'll generalize that in the next slide. So first of all, in this slide, wherever it is not working out, let us identify them and let us talk about them. Okay, here it is not working, correct? Here what is happening? Staircase is trying to catch the signal. This is the signal. This is how the signal is changing. The way the signal is changing is faster. That is why the staircase is not able to catch it. Correct or not? The speed at which the signal is going and the speed at which staircase is going, they are not matching. In the previous slides, in the previous example that I have taken, in this signal, the speed at which the signal is going and the speed at which staircase is changing, both are matching. That's why there is no error here, or error is very small. Whereas in the present discussion, in this present signal, the signal is going very fast here. That's why there is difference between the original signal and the received signal. Okay, so this difference is because of signal having higher slope, than the speed at which the staircase can go. The speed at which staircase can go, or the speed at which signal can change. These are the two important things. Speed at which signal can increase or decrease, the speed at which staircase can increase or decrease. These two speeds are important for us. So here, the distortion that we got here is because of signal speed dominating staircase speed. Because signal speed is overloading or dominating, we call this distortion. Whatever distortion we got here is because of more slope or more speed for the signal. So that's why we call it as slope overload distortion. We call it a slope overload distortion. But if you observe here, if you try to reconstruct this blue signal, what we get is, if you join the midpoints, you get some kind of changes. Here the signal is not at all changing, it is changing very slowly. But if you reconstruct this blue signal, you get faster changes than the original signal. So here also we are getting some distortion. But what is happening here? Signal is changing very slowly. Compared to the signal, staircase is changing much faster. Here also there is a difference between the speeds. In delta modulator, we get errors, we get distortion only when the speeds mismatch. Whose speeds? One is signal, another one is staircase. Signal speed, staircase speed. If these two mismatch, we get distortion. Okay, there are two ways of mismatching. One way of mismatching is signal's speed dominating. Another way of mismatching is staircase speed dominating. When the signal speed dominates, we get one distortion which we call it as slope overload distortion. And when the staircase speed is dominating compared to the signal speed, we call it as, this is also a distortion, we call it as, that is named as granular distortion. That is called as granular distortion. So in place of distortion, if somebody calls it as noise, that is completely acceptable. If somebody calls it as error, that is also acceptable. So slope overload distortion or slope overload noise or slope overload error, anything is fine. Similarly here also, granular distortion, granular noise or granular error, anything is fine. So there are two types of distortion that we get. And when do we get that? When the speeds mismatch. Okay, wonderful. Right, so let us generalize things here. Now let's come to the final point. Under what conditions delta modulator will work well? Under what conditions it will not work well? Okay, let's understand carefully. Guys, subscribe to the channel if you have not already subscribed, and hit the like button if you are liking the session. Right, now let's come to the important discussion, and that is under what conditions delta modulator will work fine. D by dt of m of t, will that give the slope of the message? Slope always will give us the speed. Slope always gives us the speed. And d by dt of, if you do take the differentiation of the message signal, we'll get the speed of the message signal or slope of the message signal, and that is what is important for us. When we are talking about speed, we are not interested in the whether it is negative, whether it is decreasing or increasing. That's not important for us. How fast it is going, how fast it is increasing or how fast it is decreasing, that is important for us. So sign is not important for us. That's why I'm taking only the magnitude of the slope. Magnitude of the slope will give us the magnitude of the speed. Right, so this is the speed of message or slope of message. And how about Can anyone tell me how about the speed of staircase signal? We want these two to match, right? For no distortion, we want the speed of message and speed of staircase to match. Correct? Whatever we have understood, the same thing we are trying to write it mathematically. So this is the speed of message. Now let us understand the speed of the staircase. What is the speed of the staircase? See this one. Speed of the staircase is within TS seconds, it can increase by delta. Every TS seconds, it can increase by delta or decrease by delta. Okay. The time taken to increase by delta is TS seconds. It's not continuously increasing. It is increasing only at certain points, but still, every TS seconds only, it can increase by delta. In less than that time, it's not possible, or greater than that time also not possible. Okay. Exactly every TS seconds, on an average, it can increase by delta. Right. Keep that in mind. In TS seconds, it is changing by delta. In TS seconds, if it is changing by delta, what is the speed? What is the meaning of speed? For 1 second, how much is the distance traveled? Meters per second. That is the unit of speed, right? Meters per second. For 1 second, how many meters of distance a person travels or vehicle travels? That is what we call as speed. The distance traveled within 1 second of time, that is what we call as speed, right? So in 1 second, in TS seconds, if it can increase by delta, on an average, in 1 second, how much it can increase? It can increase by delta by TS. Just divide both sides by TS. So in 1 second, it can change by delta by TS. In 1 second, whatever is the change, that is what we call as speed or slope. So speed of staircase is delta divided by TS. So if these two can match, what we can say is, this is the case of, under this condition we can say that there is no distortion at all in the signal. There is no distortion in the signal, right? Okay, but is that practically possible? Is that practically possible? No distortion, is it possible for any signal? Is it possible for any signal? If it is possible, can you tell me what kind of signals it is possible? For what kind of signals is it possible? If at all, if it is possible, for what kind of signals is it possible? Say this one, delta is step size. Once we design the step size, once we design delta modulator, step size cannot be changed. And once we design the delta modulator, sampling rate also cannot be changed. So delta by TS, these are constants. Once we design it, once the design is done, they are constants. We can't change them, right? So if this is a constant, this is definitely a constant. Once you design, it's a constant. In delta modulator, it's a constant definitely, for sure. In adaptive delta modulator, we do something to change it. That's a different story. So this is constant. This factor is constant. If this factor is constant, if you don't want any distortion, if this is constant, this also should be constant. Correct or not? If at all, if you can make sure that this signal, this part is constant, we can't make sure, okay? We personally can't do anything. But if the message is in such a manner that this part is constant, if this is constant, then only there is a chance that we can choose the step size in such a manner that this constant and this constant will match. If these two constants match, then only there is no distortion. This is 100% constant in delta modulator. If this is constant, this also should be constant for no distortion. So for no distortion is possible for signals which has magnitude of slope, which has d by dt of m of t modulus as constant. As constant for whatever duration they exist, because signal cannot exist for infinite duration. No, for whatever duration they exist, for that duration it should be having constant magnitude of slope. It's not constant slope, mind this, it's not constant slope, it's constant magnitude of slope. As constant for duration of time, for the duration of time it exists. For example, if I am speaking, I might speak for 10 seconds and stop it. My signal is existing only for 10 seconds. To see the slope only for that 10 seconds. Because after 10 seconds, my signal will not be there, which means the slope will be 0. Okay. For this 10 seconds, my slope is one thing, and after 10 seconds, slope will be 0. So different slopes. Don't consider that way. In whatever duration signal exists, in that duration of time, it should have constant magnitude of slope. Constant magnitude of slope or constant slope, they are different. let's say signal is there for 10 seconds. For total 10 seconds, if I'm having a slope of 2 units, that is fine. That is constant slope. Okay, constant magnitude of slope means if the signal is having till 5 seconds, if it is having a magnitude of 2, and next 5 seconds it is having a magnitude of -2. If you take the modulus, still the magnitude is 2 only, no? Okay, if the magnitude of slope, whether it might be positive or negative, but if the magnitude of slope is constant for the duration in which it exists, for those signals, only for those signals, delta modulator can work wonderfully well. But for other signals, delta modulator will fail. Okay, so it will fail. So that's why we have designed one more called adaptive delta modulator, which will overcome the problem that is there in delta modulator, right? So now we have understood for what kind of signals delta modulator will work well, and we have also understood the condition for which delta modulator will work well. Okay, the condition for no distortion, and for whatever signals, for what kind of signals the distortion will not happen, that we have understood. The signals for which magnitude of slope is constant for the duration in which it exists, for whatever signals have constant magnitude of slope, for those signals only this no distortion condition will be satisfied for delta modulator. Those kind of signals, yes, they are there, mathematically they are there, but practical signals like voice, audio, video, definitely they don't have constant magnitude of slope. Do they have? Just tell me. My message signal, voice signal, practical voice, audio, video signals, these kind of signals, will they have constant magnitude of slope? Is that possible? Just take sinusoidal signal, na? Is it having a constant slope? Sinusoidal signal is also not having a constant slope, na? Right? So sinusoidal signal itself is not having a constant slope, means how can a voice signal have a constant slope? So practical signals will not have constant slope or constant magnitude of slope. So for practical signals, there is no practical signal which can satisfy this condition. So for practical signals, delta modulator will provide distortion. Definitely there will be some distortion. Okay, which means there will be some definitely quality reduction. How much quality reduction depends on what signal is being applied. For different signals, quality reduction will be different. Okay, right. So let us talk about the other things. Okay, this is the case of no distortion. What happens? We know if this is not satisfied, distortion will happen. But there are two types of distortions, no? What are those distortions? If this is greater than delta by Ts, then what happens? Signal slope, speed of message is dominating over speed of staircase. In this case, when this is not happening, we'll get distortion. Okay, when this is not happening means either this should happen, or other thing is either greater than sign or less than sign. Only one of them can happen, right? Correct? Only these two can happen. Apart from this, only these two can happen. This is the case of no distortion, and when instead of equal sign, if you are having greater than sign or less than sign, we'll get distortions. There are two distortions. Let's match them. What is this distortion? Message slope is overloaded here. Message slope is bigger, so we get slope overload distortion. The condition, under this condition, we get slope overload distortion. And this is what we call as granular distortion. Okay, let's say we have chosen some step size. We'll have some value for some speed for the staircase. Whenever at different times message will have different slopes. At some duration of time, if the message slope is greater than this, in that duration of time, for few seconds, for few seconds, if this is greater than this, those few seconds we might get slope overload distortion. For few seconds, if this condition is being satisfied, in those few seconds we might get granular distortion. In a signal, based on how we design the step size, we might have one of these errors or both the errors also. For practical signals, we might have both the errors. Or if you choose a very small step size, then you will have only this distortion. If you choose a very big step size, then you might have only this distortion. If you choose a medium step size, then you will have both the distortions for all practical signals. Okay, right? I hope it is clear till this point. We have understood how the delta modulator works, and we have understood for what is the condition for no distortion in delta modulator, and we have understood for what kind of signals no distortion condition is possible, and we have understood the condition for slope overload distortion and the condition for granular distortion. Okay, Right. So I want to talk about one more condition here, one more condition, and that is okay. No slope overload distortion. There is one more condition based on which questions can be asked. No slope overload distortion. See, for practical signals, both distortions can exist based on how we design the step size. If the step size is designed properly, we can make sure that only slope overload distortion can be eliminated, only a granular distortion exists. Or we can choose the step size in such a manner that only granular distortion exists and slope overload distortion does not exist. Okay, we can design it that way. Okay, there is one condition which says for some message signal, they'll give some message signal in the problem, and they'll say choose some step size, design the step size in such a manner that there is no slope overload distortion. Only slope overload distortion should be completely eliminated at any point of time. At any point of time, slope overload distortion should not be there. Try to understand this. We want no slope overload distortion. When do we get slope overload distortion? When the message slope dominates. The requirement is we don't want slope overload distortion at 1 second or 2 seconds or 10 seconds, 100 seconds, 1000 seconds also. We don't want slope overload distortion. At no time, slope overload distortion should happen. Okay, which means at no time, message slope should not dominate. Correct? Message slope should not dominate. Message slope should not dominate. Since we are talking about message slope not dominating, if you don't want message slope not to dominate, then you should talk about the maximum slope of the signal, because this condition might happen when our message is having more slope, bigger slope. So if you make sure that whatever bigger slope is there, whatever is the highest slope in the message, according to that if you design the step size, then we can avoid slope overload distortion. Choose the step size in such a manner that it caters to the maximum slope of the message. So maximum magnitude of slope, it's not maximum slope, it's maximum magnitude of slope. Okay, so if the maximum magnitude of slope, if it is less, the message slope is not dominant, if staircase slope is dominant always at all times, then definitely we can avoid slope overload distortion. If it is less than or equal to delta by Ts, under this condition we can completely avoid slope overload distortion. Slope overload distortion, it will be there when this condition, it will be absent under this condition. Okay, which means less than condition should be happening if you want to avoid slope overload distortion. But since we want to avoid completely slope overload distortion, this is a constant, and if we have to take another constant here, then only we can get the condition. Okay, the idea is to design an optimum value of step size, some fixed value of step size, so that no slope overload distortion exists. So if you want to choose some constant value here, this also should be a constant value. If this is not a constant, how can we choose? Okay, so the optimum value of step size, which will make sure that there is no slope overload distortion, is when the equal to condition is happening. We can write it as delta optimum. When we write, instead of less than sign, if we can write the equal to sign, we can write the delta as optimum delta. But under this condition, no slope overload distortion exists. But the same condition I am just rewriting, d by dt of m of t maximum, I am choosing step size in such a manner that this matches with this. That kind of step size is what we call as optimum value of step size. And here also, if you can choose some step size so that this condition is happening, that step size we call it as optimum. Optimum is the best value of step size. Okay, I hope everything is clear till this point. Only 4 conditions: no distortion, slope overload distortion, granular distortion, and completely to avoid slope overload distortion. Or try to understand this. When this condition is happening, let's say some duration of time, we want to avoid this now. I am explaining that again in a little different manner. You want to avoid slope overload distortion. Slope overload distortion happens when this condition is being satisfied. You have chosen some step size. So when you choose the step size, message slope is dominating. To increase this, if you can choose a bigger step size, then this value will increase. If this increases, this condition may not happen now. As you increase step size, speed of the staircase increases. As you increase the step size, speed of the staircase increases. If the speed of staircase increases, message need not dominate the staircase. Okay, message need not dominate the staircase, right? As you increase the step size, the domination of message over staircase will stop. So as you increase the step size, slope overload distortion decreases, correct or not? As you increase the step size, these two slopes become closer, then slope overload distortion will decrease. But as you decrease the step size, granular distortion will decrease. But as you increase the step size, slope overload distortion decreases, but granular distortion increases. I'll just show you an example. Let's take an example. See this one. In this case, in this one, if you take a bigger step size, it might follow the signal. No? If you take a bigger step size, the staircase will follow the signal. You have to choose the step size appropriately. If you have chosen the step size appropriately here, if you have to choose a bigger step size, it will follow the signal. But if you choose a bigger step size, here there will be more error because the granular distortion will increase. See, if it is a bigger step size, it will go like this. Bigger error will be here. As you increase the step size, slope overload distortion decreases, because as you increase the step size, we are increasing the slope of the staircase or speed of the staircase. As you increase the speed of the staircase, slope overload distortion decreases, but granular distortion increases. Similarly, here, see this one here. Here, if you can decrease the step size, if you can make sure that the step size is smaller like this, then the distortion will decrease here. So you can decrease the granular distortion. You can decrease the granular distortion by decreasing the step size. But when you decrease the step size, if you decrease the step size, then slope overload distortion increases. Okay. So delta increasing, one distortion will decrease, another distortion will increase. Okay. So when you change the delta, one distortion decreases, another distortion increases. So we can't avoid the distortions completely. But what we can do is, the problem can be asked in this way. Anyway, we can't avoid both the distortions for any practical signal. So at least avoid one distortion completely. Okay. So if you want to avoid distortion, this is maximum value. Okay. So choose a value which is equal to this or greater than this. Okay. As you choose bigger value of step size, we can definitely reduce the slope overload distortion. But they may not ask you the question on no granular distortion completely. If you want to reduce the granular distortion, the simple funda is we have to reduce the step size. As simple as that. The smaller the step size, smaller the granular distortion. But if you write a condition, you might say, sir, this is a minimum value of message slope. Minimum value you'll say, because if you don't want granular distortion, you want smaller value of step size. Okay. If you are talking about smaller value of step size or smallest magnitude of slope, smallest slope will become generally 0. If it is 0, step size chosen should also be 0. If step size is 0, it will not follow the signal at all. No, it will not change at all, right? So that's why they will not ask you a question on no granular distortion. They will ask you questions only on no slope overload distortion. But we may not be able to, because we'll get if you do the calculation, we will get it as 0. So, but what we can do is, if you want to reduce the granular distortion, we can choose the step size as small as possible. That much we can do. For no slope overload distortion, you can follow that condition. Yes, wonderful questions can be asked. Any question asked on delta modulation will be based on these conditions. Very, very important slide. All the questions that can be asked from delta modulator are in this slide. Okay. Praveen, I'll get back to you. Give me a minute. Right. So these are the homework questions that I am giving you for tomorrow. Yeah. Whatever I've discussed in this today's session. Based on that, you should be able to solve these questions. Okay. So you can note it down now, or after the class also you can get back to this place in the video and you can note it down. And don't forget to post the answers in the comment section. Don't forget to post the answers in the comment section. So if you have not subscribed to our channel, please subscribe. And if you like the content that is provided in this session, please like the video. Okay. So that's it for this session. In tomorrow's session, we're going to discuss wonderful questions based on delta modulation. Tomorrow is a practice session. So I'll discuss all the models possible on delta modulator. Okay. Right. So let me come back to Praveen before leaving. Praveen, your rank is 131313. I'm 2021 passed out. Why do you want to drop, Praveen? 1313 is a wonderful rank. Why do you want to drop? There is no need to drop. Carefully apply for colleges. See, I'm going to take a session tomorrow. I'm going to take a session along with one of my student who has done masters. He's just now completing his masters. He's in the second year in some college in NIT Trichy. He's placed with a 40 lakhs package. So I'm taking an interview session with, not interview actually, it's a guidance session for you guys. So for what ranks, for what colleges you have to apply, that is one thing. And we're going to cover a lot of things, a lot of unknown branches. With the ranks like 1300, 1500, 2000 also, there are wonderful opportunities available. So to make sure that you guys are aware of all those things, I'm taking a session tomorrow. So don't miss that session. And we are also going to cover some unknown branches, which are very, very important branches, which can give wonderful packages, wonderful placements. So we're going to discuss that. And should you choose for college or branch? So you got some college, some IIT, but you did not get a required branch. But you got some, a college which is lesser than that, maybe some NIT, but with a better branch. So how to choose, which one to choose. And one more thing I'm going to cover is, let's say you are in third round of counseling, you got some college. Should you stick to that option, or should you go to the next round? Should you wait for the next round? So students will have a confusion. We'll give some wonderful guidance in tomorrow's session. So everything will be clear in tomorrow's session for you guys if you guys are applying for colleges. If you're applying for college next year also, this session will be useful for you. Okay, next year also when you are applying for colleges, you can go through the session that I'm going to take in tomorrow at 10 p.m. I'm going to take that session, that guidance session. But today, so tomorrow also technical session is there, the practice session on delta modulation at 8, and at 10 it will be the guidance session. So don't miss that. So like the video and subscribe guys. And Kiran, hi. Praveen, I hope it is clear. Tomorrow everything will be clear, okay? So I'll make sure that you can ask the doubts. You can come to the live session, you can ask any doubt that you have, okay? Everything will be here, and you can follow me on Telegram, and you can ask me doubts on Telegram. I'll be there to help you. Don't worry. Okay? Right then. Good night. Take care. Bye-bye. See you tomorrow.